Hi everyone. Today we're going to look at some measures of central tendency and dispersion, ways to sort of describe sets of data. And you're probably already familiar with some measures of central tendency. The ones we're going to focus on today would be the median, which would be the middle value in a set of values, and the mean. Mean we often call average. That is when we take the sum of all the values and divide by how many values we have. And these descriptive statistics can tell us a reasonable amount about a set of data, but they are limited. So to show that, let's look at these two sets of data here, A and B. So let's say we have 6 students who've written a quiz. And on quiz A, all 6 students have gotten 75%. On quiz B, 3 of them get 50 and 3 of them get 100. Now in both cases, so in the case of A and in the case of B, in both cases, we're going to have the same median. Because if we look at A, well, obviously the median is 75 because all of the values are 75. So the 2 in the middle would also be 75. For B, the 2 values in the middle are 50 and 100. So when that happens, that we have 2 different values in the middle, the median is then the number halfway between them. So 75 is the number halfway between 50 and 100. And when we're trying to calculate the mean, so this is one of the symbols for mean, I'll talk about the other in a moment. When we're calculating the mean, well, if I add up 75 6 times and then divide it by 6, I'm just going to get 75 again. If I add up 50 plus 50 plus 50 plus 100 plus 100 plus 100, and I divide that by 6, I also get 75. So the central tendency is actually only telling me half of the story. On these 2 quizzes, the middle of the data is in exactly the same place, but obviously they're really different sets. So we need some measures of dispersion. Before we do that though, I'm going to just quickly, there are 2 different notations for mean that we're going to use kind of interchangeably. They do have a slightly different use, although that detail doesn't matter in this course. So there's the X with the bar over it, and there's the Greek letter mu. So in the first case, this is for if we are taking the mean of a sample. And in the second, this is for if it is the mean of the entire population. We are always going to assume in IB that we have the full population. So we should, in theory, always be using mu, but we'll use them both kind of interchangeably. It's just when you get into a university stats course, they're going to be much more particular about the difference between those symbols, although both of them are calculated in exactly the same way here. We add up all the values, we divide by the number of values that there are. The other thing that we need, though, to talk about is dispersion. So as far as dispersion goes, we're going to look at essentially 2 different measures. One of them is a pretty straightforward one, and it's easy to calculate, but it is of slightly limited usefulness, and that is the idea of range. So the range of a set of values is very simply the maximum value minus the minimum value. So it's a pretty rough indicator, but it does the trick. So for A, I can tell that I have a range of 0 because it's just 75 minus 75. There is no maximum or minimum. They're all the same. For B, on the other hand, my range is 100 minus 50, so we have a range of 50. So right off the bat, that gives us a difference. We say that the values for B have a much wider range than the values for A. It's still only a part of the picture. Its usefulness in that it's very, very quick to calculate, but it's a little more limited. So that is where we go to variance, and much more commonly used but very closely related to variance, we have what is called the standard deviation. Both of these words actually do tell us a little bit about what they're measuring. Variance, measuring how much variety or variation there is in our data. And standard deviation, deviating, when something deviates, it moves away from. So we're essentially measuring what is the standard deviation from the mean. In other words, how far away are the values from the mean? And again, we have different symbols whether we're dealing with a sample or a population, except in this case, they are actually calculated differently. So variance is S, or this sigma squared. And again, this would be for a sample. It does have a slightly different formula, and we are not going to use it in this course. We're going to always assume we have the whole population. So we are always using this sigma one. And standard deviation is the square root of variance. So standard deviation would be just S or sigma. But again, we're not really going to use the S. We're only going to use the sigma because we are always assuming we have the whole population. And here is the formula. Sigma squared is the sum from 1 to n of xi minus mu, all squared, divided by n. And then for standard deviation, I would just take the square root of both sides. So to be clear on what this is calculating, xi, these are the individual values. So for each individual value, I subtract that number minus the mean, and then I square it. And the reason we square it is essentially so that we do not have to worry about whether it's positive or negative. Because if a value is above the mean, then xi minus mu is going to be positive. If it's below the mean, then the subtraction will give me a negative number. But as soon as I square it, then that doesn't matter. But that's why variance is a squared value, because we've squared these. And then we divide by n. So that's essentially giving us the average distance between each value and the mean. So for A, so for my first distribution here, essentially the variance is each value, which is always 75, minus the mean, and there's 6 of them, so 6 times that, squared, divided by 6. Well, 75 minus 75 is 0. Doesn't matter the squaring, the times 6 to divide by 6, it just ends up equaling 0. So the variance is 0, and at the same time, the standard deviation is also 0. Which again, makes sense if I think about standard deviation as being the average distance between the values and the mean. It's not exactly that, but it's pretty close to that. That's a helpful way to understand it. The average distance between the values and the mean here is 0 because all of the values are at the mean. For the second distribution, on the other hand, the variance would be 3 times the 50 minus 75 squared plus 3 times the 100 minus 75 squared divided by 6. Now, in this case, 50 minus 75 is going to give me negative 25, but as soon as I square that, it becomes positive. And 100 minus 75 is going to give me positive 25, but as soon as I square it again, I get 625. So ultimately, I have 6 times 625 divided by 6, which is 625. So the variance is 625, quite a bit larger than in the first case. And in fact, the standard deviation is the square root of that, 25. Not a shock, because all of the values are either exactly 25 less than the mean or exactly 25 greater than the mean. So the average distance between my values and the mean is 25. So that's the standard deviation and the variance. That's how they're calculated. Now, I show you the formula in order to help you understand what it is this is measuring. But in fact, you don't need to calculate them by hand. So we're going to look at how we can calculate them using technology. But first, I want to look at how we often group our data. So in this case, because I only had 6 numbers, it was easy to just deal with them as they are. But in cases where I have a wider range of numbers, I usually group that into a frequency table. So I've got 2 different types of frequency tables here, a discrete frequency table and a continuous frequency table. So let's look at the discrete one first. So here this is representing the number of times a team scored a certain number of goals per game, let's say. So in 17 of their games, they scored no goals, 25 they scored 1 goal, 21 games they scored 2 goals, etc. So this is grouped. Rather than just having a list where I write 0, 0, 0, 0, 0 17 times, and then 1 25 times, we group it. In our calculators, we can do this same thing. So I'm going to show you on the TI-84. If you have a different calculator, you can look it up. It's very similar. But essentially, I go to Stat, and I have to enter this information in Stat. On the TI-84, that's under Stat Edit. And I'm going to put the actual values themselves, so in this case, the number of goals, into list 1. And then I put the frequencies into list 2. Once I've done that, I quit out of the editor, but I go back to stat because I want to do a calculation, and we just want to choose the very first option, one variable stats. Now, if you have a stat wizard, you'll notice that you have a choice for list, frequency list, and then calculate. Mine already is filled, so list is L1. That is where I put the actual values. And frequency list is L2. So if you don't have something there already, you'll have to go and put list 2, L2 in the frequency list, and then calculate. And I get a whole bunch of information. The ones that are relevant to me. The mean is 1.5125. I scroll down a little. This gives me the sum of all the values is 121. That's useful sometimes. It's not useful for us right now. The sum of all the squares is 283. Then it gives me SX and sigma X. Remember I said they are slightly different. We're ignoring the S. We want the sigma. So sigma in this case is approximately 1.11796, etc. So to 3 significant digits, 1.12. N is 80, so what that means is if I were to add up all of these, this table is representing a total of 80 games. And I can see the minimum, I can see Q1, median, Q3, and max. We will come back to that with a different set of data and talk about what that is, but you can scroll through all the information that it gives you. For this, I can also sort of visually see what's going on with this distribution by using a bar graph. So I don't have grid lines here, so it's not going to be super nice, but let's say I have 0 goals is 17. I've got 25 goals, or 25 times I got 1 goal. 21 would actually be exactly halfway between 17 and 25, so that should be kind of there-ish. Just as an example. And that distribution, that bar graph, can help me see roughly where the center of the data is. So I would sort of, looking at that table, think, okay, yeah, the data has a center sort of here-ish. And I can see that it is distributed, so on average, within 0 to 3. So if I add the standard deviation to the mean, that kind of gives me a good idea of where most of the data will be, and I subtract it. So I see that this data is grouped a lot in the 0, 1, 2 region. Now, the other type of frequency distribution is if I have continuous distributions. So yes, when I score goals per game, I'm either scoring 1 or 2 or 3. I'm not scoring 3.7. But something like a height distribution is going to be much more varied. So it maybe isn't helpful to have every single individual thing have its own distribution. So here we can group it into intervals. Now, if I were to represent that on a graph, I would use a histogram, which is a type of bar graph. Oh, that's terrible. Not a straight line. So let's say I have 50, 55, 60, 65, 70, 75, 80, as an example. So if I only have one between 50 and 55, I show that by making the bar run from 50 to 55. And then 8, and then 19, and then 7, and then be careful because there's nothing between 70 and 75, and then 2 between 75 and 80. So this right here shows me I'm expecting the middle of this data to be somewhere kind of in here, so the 62, 63 range, and that this data is more grouped around the middle. But how do I do this in my calculator? Okay, so let's go back to stat edit. We're still going to be doing a frequency list. So in list 2, I want the frequencies. So 1, 8, 19, 7, 2. But over here, I can't put an interval. So I can't actually put 50 to 55. So we kind of cheat a little and we use the central point. So 52.5 is in the middle of that interval. So I'm going to put 52.5. Then 57.5, 62.5, 67.5. There's no 72.5 because I had nothing in that interval. So then 77.5. So I'm only going to get an estimate. It's not going to be exact because I don't know all the specifics. But essentially what I'm doing is I'm assuming that all of the values in the 60 to 65 range are actually 62.5. So of those 19 values, I'm saying, what if it's just 19 people with a height of 62.5 inches? Now that is a bit of an assumption on my part that's probably not true. So this isn't going to give me necessarily the most exact calculations, but it's going to be pretty close because odds are the same number of them are less than like 62.5 as are greater. The other thing I want to draw your attention to is where the boundaries are included. So I have less than or equal to on this side, but just less than on the other one. So in other words, if a person had a height of exactly 55 inches, then they would be included in the second interval, not in the first one. If they were 54.9, they would be included before that. But as soon as they're exactly 55, they're included in that second interval. If they're exactly 60, they jump up into the next interval. So be careful where you're less than equal to. I need to know exactly where I would put exactly 55. All right, so now that I've entered my data into the list, I'm going to quit out of there, go back to stat, calc, one variable stats. I've got list 1, list 2 for my frequency list, and I calculate. So here we've got a mean of approximately 62.9 inches. And we've got a standard deviation of 4.98 inches, roughly. So that means that on average in this distribution, I'm expecting that people are about 62.9 inches tall, and that most of them are going to be within about 5 inches of that. So 5 less than 62.9, 5 more than 62.9. That's where I'm going to find the vast majority of the values. Another way to represent this is using a box and whisker plot, and this is where we use the minimum, Q1, median, Q3, and maximum. So that's where we use that information. So we'll pull that information from this heights distribution as well. So now if I scroll down a little further, I see I've got 52.5 is the minimum, but I actually know that my minimum is 50. So I am overriding the calculator here and saying, yeah, the calculator thinks 52.5 is the minimum because that's what I entered, but I know for my table that 50 is the minimum. Likewise, I know that the maximum is 80, even though the calculator has 77.5. But for the other ones, I'll go with the calculator. Q1 is 60, the median is 62.5, and Q3 is 65. Now, what do Q1 and Q3 mean? Well, Q1 is the first quartile. It's basically the median of the first half of the data. So 25% of the numbers are less than Q1 and 75% of them are greater than Q1. And Q3 is the third quartile. So basically the median of the second half of the data. So 75% of the numbers are less than 65 and 25% of them are greater than 65. So Q1, median, and Q3 basically divide my data into 4 groups, 4 equal groups. I just also wanted to comment here, I can see N is 37, so that means that in this case, I'm talking about a distribution of 37 people. That's what I would get if I added all the frequencies together. All right, so now, what does the box and whisker plot do? Well, the box and whisker plot takes this information and represents it essentially on a number line. So I have a number line, 50, 55, 60, 65, 70, 75, 80. And what we do is at our minimum and maximum, we have dots. Those are going to be the edges of my whiskers. The box covers Q1, median, and Q3. So from Q1 to Q3, I draw a box. And at the median, I draw a line in the middle of that box. So Q1, median, Q3. So the box contains the middle half of the data. And then I draw the whiskers, so the lines, out to the minimum and maximum. So that is a box and whisker plot. The skinnier the box is, the more clustered around the middle that half of the data is. So if I have a big wide box, it means the numbers are distributed. And if we have long whiskers, it means there's quite a long dispersion. But we can also use this information to mark what are called outliers. So outliers are values that are outside of the median plus or minus 1.5 times the interquartile range, which I'll call IQR. So interquartile range. The interquartile range is simply Q3 minus Q1. Remember, the range of a distribution was the maximum minus the minimum. The interquartile range is the third quarter minus the first quarter. So in this case, 65 minus 60, the interquartile range is 5. So the outliers would be outside of the median, which is 62.5, plus or minus 1.5 times the interquartile range, which is 5. So that's 62.5 plus or minus 7.5. So in other words, if a value is less than 62.5 minus 7.5, which is 55, or greater than 62.5 plus 7.5, which is 70, it is an outlier. So in this case, anything outside of these blue X's is considered an outlier. In the table that I have above, I can see that I have one value that's less than 55 and two values that are bigger than 70. So in this case, we actually have 3 outliers. It's not that we throw them out of the distribution, it's just that there's something about them that is outside the normal range that we expect to see. So there is some practice for this on a worksheet in D2L. Practice with your calculator. If you have a different type of calculator, you might have to look up exactly how to do it, but you don't need to be able to calculate standard deviation by hand. You do need to be able to interpret what you're getting and know that you can get all of those different statistics.